Very well. This screencast gives me an opportunity to hit a couple of examples, one that's pretty straightforward that I hope you'll be able to follow with no trouble, and one that gets a little bit more difficult because, well, hey, we should deal with things that get a little bit more difficult. So let's take this region. This is the region bounded above by square root of x and below by 1/2 x. That seems fair. This is the region. We're going to revolve that about the y-axis and ask for its volume. So again, we imagine that the solid itself is some cone, right? It's some cone, but there's a solid that's been removed from that in the shape of some sort of board game piece or maybe a chocolate candy or something like that. So there's a solid that's been removed from the cone that gets generated when you take the line and spin it about that axis. So how do we do this? Well, our slices are parallel to the axis of rotation, so they are paper towel rolls, and so we can use the method of cylindrical shells. That's the integral of 2 pi radius, height, thickness. The radius of the paper towel roll, well, the A radius of the paper towel roll goes from 0 to whatever this x value is. The radius is the x value. The height of the paper towel roll appears to be the difference between the blue function and the red function. And then the thickness is dx. From where to where? Well, we'd need to know where these two curves cross, and I don't think I'm talking out of school if I say that that interval runs from 0 to 4. So how does this happen? Well, there is no product rule for integrals, so we distribute the x, we distribute the x, and then it's fundamental theorem part 2. You find an antiderivative, we find an antiderivative, we substitute, and subtract. Let's see, so 4 to the 5 halves, that's the square root of 4 raised to the 5th power, that's 2 to the 5th power, that's 32, times 2/5 is 64 fifths, and 4 cubed is 64, 64 sixths is 32 thirds, and whatever that turns out to be, it is. That's not the important part. The important part is this setup, and the important part is knowing how to find antiderivatives so we can use the fundamental theorem part 2. Okay, so just a reminder that the height of the paper towel roll is not always one function. Sometimes it is the difference between two. One other thing to draw out for us. Let's take the region bounded by y equals x plus 1 and the x-axis from 0 to 2. Let's take this region, but then instead of revolving it about the y-axis, let's make our axis of rotation x equals 2. You sort of imagine you get the top of a crayon, maybe. That seems to be the way to go with that. What's the volume? Well, our slices go parallel to our axis of rotation, and so we end up with a paper towel roll, and the volume of a paper towel roll is an integral across our region of 2 pi times the radius times the height times the thickness. So what's the radius of the paper towel roll? Well, the radius of the paper towel roll goes from 2 down to whatever this x value is. So the radius is not x as it has been in every other example. It is this distance, and this distance is 2 minus x. The height of the paper towel roll, this height, appears to be a function value, so that works out okay. And then we just do a little bit of algebra. This is 2 plus x minus x squared. And so the fundamental theorem part 2 says we find an antiderivative, we find an antiderivative, we find an antiderivative, and we evaluate at 2, at 0, and subtract. No surprises here. It's not terribly complicated to crank out. This is the method of cylindrical shells. This is about as hard as I can make it. It's always 2 pi radius, height, thickness. Always, always, always. So I hope that these are a representative sample of the kinds of things that you can expect to do. There are plenty of questions to practice with in our textbook. Hope to see you soon in person.